Transformations, one of the most elegant and most poorly presented topics in high school math classes. In a standard high school curriculum, transformations are taught in several contexts and multiple grades. Every time, the students attempt to memorize a litany of mismatched rules that they don't really understand, and every time they forget these rules before they have to relearn transformations. The instructions for transformations change based on which application you're dealing with. Some explanations that you may have heard for dealing with transformations are: you use order of operations for y, but for some reason, you're supposed to use reverse order of operations for x. Also, you can't just use order of operations if y isn't isolated on one side. In other words, if it's inside the function without extra parentheses, do shifts before stretches, but if it's outside, then do stretches before shifts with a lot of exceptions. If you get confused, just start plotting points and you'll get it. When in doubt, which is often, plot it out. Or, I have a completely original method that explains everything that you need to know about transformations in under 10 minutes with just 2 rules. 1. Change the variables. 2. Shifts last. The CVS method, and not the one that the pharmacy uses. Remember, the graph of an equation is the set of all points that make the equation true. For example, 2, 8 is one point that makes the equation y equals x cubed true. The key to being a master of transformations is understanding how the x and y coordinates need to change in order for the equation to remain true. We already have y equals x cubed written, so let's discover the graph of y1, the new y coordinate, equals x cubed plus 1. The question is, what does the new y coordinate have to be in terms of y, the old y coordinate, in order for the equation to remain true? Well, we added 1 to the right side of the equation, so we must add 1 to the left side, so y1 must equal y plus 1. What happened here is the x coordinates stayed the same as they were, but every new y value must be 1 more than the old y value for the equation to remain true. In other words, all points in the graph simply move up by 1 unit. Again, looking at y equals x cubed, say that we want a graph of y1 equals 2x cubed. What does y1 have to be in terms of y? Well, we multiplied the right side by 2, so we have to multiply the left side by 2. Each new y coordinate is twice the old y coordinate. This is called a vertical stretch to twice the height. Now consider y1 equals negative x cubed. What does y1 have to be in terms of y for the equation to remain true? If you said negative y, then you were right. In other words, all of the x-coordinates stay the same, but the y-coordinates become negative of what they used to be, which implies a flip over the x-axis. Next, let's look at some horizontal transformations. What if we want to graph y equals x1, the new x-coordinate, plus 1, quantity cubed? The y-coordinate stays the same, but the x-coordinate becomes the new value, x1. What does x1 need to be for the equation to remain the same? The new x values have to equal the old x values, minus 1, because if we plugged in x minus 1 in place of x1, then the equation immediately simplifies to the original. In other words, the graph shifted left 1 unit. How about y equals 2x1 quantity cubed? What does x1 need to be in order for the equation to remain the same? X over 2. If you plug in x over 2 instead of x1, then the equation would immediately simplify to y equals x cubed. In other words, we have a horizontal compression to half the width. Finally, let's graph y equals negative x1 cubed. What does x1 have to be in terms of x in order for the equation to remain the same? Negative x. The y-coordinates remain the same. The x-coordinates become negative of what they used to be, so the graph flips over the y-axis. That's it. You now know how to do all of the basic transformations. Now prepare to be amazed. Let's derive point-slope form of a line using transformations. You may remember that this appears as y minus k equals m quantity x minus h. We start with a line of y equals x. We're going to do all of the transformations in just 2 steps. Our first step is to graph the equation y1 equals mx. What does y1 have to equal in terms of y for the equation to remain true? We multiplied the right side of the equation by m, so we must multiply that left side by m as well. Therefore, y1 equals my. We have a vertical stretch to m times the height, and of course, if m is a negative number, then there will also be a flip over the x-axis. Wow, this explains the concept of slope! Finally, we do the shifts. y2 minus k equals m quantity x1 minus h. We use y2 to symbolize that we have a new y value, and x1 to symbolize the new x value. What does y2 have to be in terms of y1, and what does x1 have to be in terms of x for the equation to remain the same? y2 must be y1 plus k. x1 must be x plus h. The equation will immediately simplify to y1 equals mx. Now hold on to your seats for this one. Watch as I derive the equation for an ellipse from the equation of a circle of radius 1 centered at 0, 0. Consider any point x, y on the circle. The length of one leg is x, the length of the other is y, and the hypotenuse equals 1. Therefore, x squared plus y squared equals 1. We just derived the equation of a circle of radius 1 centered at the origin. Let's take the circle and stretch it horizontally to a times its width and vertically to b times its height. That would be x1 over a quantity squared plus y1 over b quantity squared equals 1. Why? In order for the equation to remain true, x1 must be ax, and y1 must equal by. Of course, that can be rewritten as this. Now, if we want to shift it so that its center is at h, k, we just write x2 minus h quantity squared over a squared plus y2 minus k quantity squared over b squared equals 1. What does x2 have to be for the equation to remain the same? x1 plus h. Similarly, y2 must be y1 plus k. You can see that we shifted right h and up k. And now we have derived the general equation of an ellipse. Other conic sections can be derived similarly. Here's an interesting way to find the area of an ellipse. Imagine we have our unit circle and we break it up into a grid of tiny squares. If each square has a side length of s, then each square has an area of s squared. Remember that the total area of a circle is pi. To produce an ellipse from the circle, all we did was stretch the circle horizontally to a times the width and vertically to b times the height. So each of these squares was similarly stretched. The width was s, now it's as, and the height is now bs. The area of each rectangle is now ab, s squared. The area of an ellipse is pi ab. The second best way to derive this involves at least 2 pages of tedious calculus. Let's look at one final example. This time we'll use actual numbers. The graph of y equals sine x looks like this. Its period is 2 pi and its amplitude is 1. If we want to graph y equals negative 2 sine quantity negative 3 quantity x plus 4 all minus 5, it looks pretty terrible. But we can do it in just 2 steps. Step 1, flips and stretches. Graph y1 equals negative 2 sine quantity negative 3 x1. What do x1 and y1 have to be for the equation to remain true? y1 equals negative 2y, and x1 equals negative 1/3 x. This implies a flip over the x-axis and a vertical stretch to 2 times the height. It was also flipped over the y-axis and smushed to 1/3 the width. Step 2. What do y2 and x2 have to be in order to keep the equations true? x2 has to be x1 minus 4 to compensate for the plus 4. y2 has to be y1 minus 5 because we subtracted 5 from the right side, so we must subtract 5 from the left side. In other words, we shifted the graph left 4 units and down 5 units. And by thinking about these transformations, we can clearly see the new amplitude is 2 and the new period is 2 pi over 3. Now you can see that by using this elegant approach to transformations, there's no need to memorize a litany of confusing rules. Just remember, change the variables, shift last. CVS.